So we're going to start on chapter 15, and you're probably going to want to pause this video. I'm going to try to keep it to to as quick as I can, just because the longer the video, the longer it takes to upload to YouTube. So feel free to pause as we go through to fill in your notes. So in this chapter, we're essentially going to start off with some geology. We're moving out of space and talking about Earth. And so the Earth is made up of a non-uniform distribution of matter, meaning if I go and grabbed a scoop of Earth, it would be different than if I grabbed a second scoop of Earth. So it's not uniformly distributed. We know that the Earth is made up of a molten core that contains the most heavy elements that we see, mainly iron and nickel. And the crust of Earth is thinner and kind of like an outer shell, like an eggshell, and it's made up of mostly lighter elements. And if you remember, we talked about 8 elements making up almost 99% of Earth's crust, and the majority 2 being oxygen and silicon. And this is Earth's crust, and this would be if we took into account the whole Earth. Iron would be the predominant element. Now, the crust of Earth is made up of rocks and minerals, which we're going to see how those are different in this chapter. So minerals, the Earth science definition is it's naturally occurring, meaning it's not made in a lab, not made by man. It's a solid material, either an element or compound with a constant chemical composition that's found in a crystalline structure. So we see here, this is very uniformly distributed, kind of like putting Legos together. Cannot be synthetic, and it must have a regular repeating pattern. And so the example we see here is NaCl, which is called halite. Crystal structures can be made up of one or more kinds of elements. So for example, diamonds, carbon only. Quartz are silicon and oxygen in some sort of formula pattern to make up quartz. Each mineral is going to have its own chemical composition or range of chemical composition, and the composition can vary with the substitutions of very similar elements, meaning I can take silicon and oxygen and combine them with something like iron and make ruby, or something totally different than just quartz. Minerals can be classified in multiple ways, but the biggest way is to determine whether they're silicates, so this would be something that contains silicon and oxygen, or whether or not they don't contain silicon and oxygen. We can make further divides that silicates can be ferromagnesian, non-ferromagnesian, so this would be iron and magnesium. These right here would have no iron or magnesium, and then we have clay materials. The non-silicates, we have more subgroups. We have carbonates, oxides, phosphates, sulfates, sulfides, halides, and native elements. And so these are sorted by basically what they're made out of, whether they have sulfate groups, sulfides, halogens, and so on and so forth. So silicates contain mostly silicon and oxygen, and silicates make up 92% of Earth's crust, and it's based on what's called the silicon-oxygen tetrahedral. So it kind of looks like a pyramid, with silicon at the center and oxygen, 4 of them, at each corner to make kind of like a pyramid, but it's only 3-sided pyramid. It's called tetrahedral because this means 4 faces. So if we think of 1, 2, the one on the bottom, 3, and the one on the back side is 4, it's a 4-sided pyramid. Silicates can be broken up into ferromagnesian, non-ferromagnesian. If they're ferromagnesium, they contain iron, magnesium, calcium, other elements. Typically, they're darker in nature, so some examples would be augite, hornblende, and olivine. Non-ferromagnesians tend to be lighter in color, lower in density, and some examples are muscovite, feldspars, and quartz. Non-silicates do not contain the silicon-oxygen tetrahedrals, and they make up the other 8% of Earth's crust, and there are 8 groups. And these are the 8 groups, with carbonates being the most abundant. This sounds like a fun fact, but fun facts are always good to know. Easy multiple choice question, true, false, on an exam. Rocks are going to be an aggregation of one or more minerals and perhaps other materials. So, elements make up minerals, and minerals make up rocks. Now, minerals are going to be physically combined to make rocks. So, we're not talking about a chemical bonding, we're talking about a physical interaction between minerals to make a rock. Because most of our crust material is made out of silicate minerals, most rocks are also made up out of silicate materials. Now, rocks are classified based on where they are formed, and we have three main groups of rocks: igneous, sedimentary, and metamorphic. Igneous rocks are formed from magma above or below Earth's surface. So, because of this definition, all rocks at some point in their life cycle are going to have been an igneous rock. Approximately 2/3 of Earth's crust is made up of igneous rocks at this moment. The two most common forms of igneous rock that we see are granite and basalt. Granite is the same granite like granite countertops that you may be familiar with. They tend to be lightly colored, tend to be made up of three silicate minerals: quartz, mica, and feldspar. And they have visible grains, which is what people may or may not like about quartz, is the visibility of certain grains. Basalt, on the other hand, is the most common volcanic rock. Dark, more dense. The grains in a basalt rock are too tiny to see, so it would just look like a black rock, charcoal, whereas granite, you have very visible pieces, chunks of different colored materials inside the granite. Sedimentary rocks are our second group. These are formed from particles or dissolved materials from previously existing rocks. Sediments are accumulations of silt, sand, other materials that settle out of water. And these are all examples of sedimentary rocks. Excuse me. So basically, sedimentary rocks are formed from the wearing away. Lithification is is going to be essentially our rock forming process. And there are two main parts of rock forming processes. The first is the compaction, where we reduce the thickness of the deposit. We're squeezing out the water that's between the rocks, so this is coming out. And then cementation, where we have spaces are filled in using sedimentary particles filled in with a chemical deposit, and the chemical deposit binds the particles together. So we could say this was granite, different little minerals. We see gray, white, and pink, and eventually over time the spaces between the minerals become smaller, and then eventually they fill in with some sort of cementation type material and make a big nice block of granite. Now, metamorphic rocks is our third group, and these are previously existing rocks that are changed by heat, pressure, or hot solutions into distinctly different rocks. So they go through a process of metamorphoses, like the butterfly coming out of the cocoon. That's a metamorphic process. This is usually associated with geologic events, so big movement of the crust, heating and hot solutions from magma intrusion. The thing is that the temperatures and the pressure must be high enough and hard enough that it causes recrystallization but not melting. So the rock has to be able to reform. It can't just be melted into like liquid magma. This leads us to the rock cycle, where rocks are transformed into new types by Earth's interior and exterior dynamical processes like moving continents, seas advancing and retreating, weather and erosion due to wind and rain. So you can see here, this is an example of the rock cycle and how we have igneous, sedimentary, and metamorphic rocks related to each other. So now we're going to talk about some of these processes. So we use seismic waves to reveal Earth's interior. We have two different types of waves, a P wave and an S wave. P waves are longitudinal, they're compressional, they are the fastest waves, and they move through the surface rocks and interior solid and liquid materials. Transverse waves, on the other hand, are called shear waves. They are second fastest, but they do not travel through liquids, so that makes them unique, okay? Another type of wave that we have is an up and down wave, where you have a crest and a trough, just like a wave. They are surface waves, much like water waves. You can visually see them moving if you were in something like a earthquake, and they are the slowest of the other two. And these only occur where S and P waves reach the surface. So these are above surface, the other two are below surface. There are two types of waves that we see, love waves and Rayleigh waves. Love waves are horizontal S waves, they move side to side. And Rayleigh waves are like rolling water waves, more destructive. Okay, so if you imagine a road that used to be straight, eventually with the love waves it would become curved. So destructive, but not nearly as destructive as the Rayleigh waves. So we use these waves to help us learn about Earth's internal structure, which we can't see. And we know that we have three main zones. We have the crust, which is the outer thin shell like an egg, the mantle, which is much thicker than the crust, so right here, kind of like the liquid around the yolk of the egg, and the core is the central part. And we're actually going to have two parts of the core, the inner and the outer core. So we know that the crust covers the entire Earth. We have two different types of crust. We have the oceanic crust, which is the crust found under the ocean. It's very dense. It's made out of basalt rock, and it's much thinner than the continental crust. Okay, so continental crust is where we have all of our continents. It's made out of granite rock, which is very much less dense and thicker. Now we're going to have the mantle that's located right underneath the crust, but there is going to be this thing called the mohorific discontinuity, which is the mantle crust boundary. And what we know is that seismic wave velocity increases sharply from the crust into the mantle. Okay, so there's just this little layer in here, where the waves traveling through all of a sudden travel much faster once they go from the crust to the mantle, telling us that they're made up of different materials. So the mantle is the thick shell between the crust and the core, makes up 80% of Earth's volume, accounts for 2/3 of Earth's mass. It's composed mainly of olivine, which is a ferromagnesian silicate. We have three data sources that tell us about the nature of the mantle. One is seismological data, so using P and S waves. The other is the nature of meteorites, so things that come in from outer space. And we also know something about the materials that are ejected by volcanoes, because these are coming from the upper part of the mantle. Now, basalt correlation is that there is that it's close to the silicate chemical composition of stony meteorites, and it's the most common volcanic rock, and so therefore we deduce that the basalt is going to be present in the parts of the mantle, along with the olivine. So the core, the very, very center of the Earth, it makes up 15% of Earth's volume and 1/3 of Earth's mass. So the crust, even though it's important and we've never actually gone down deep enough into the crust to reach the mantle, it is such an insignificant portion of Earth's mass and Earth's volume. So what we used is P wave seismological data. So if they started off, say like an earthquake here, putting off P waves, and then they tried to detect the waves across the Earth, they saw here that the P waves were deflected as expected. But however, the P waves that went straight down and interacted with the core, they started doing some interesting things, which was they resulted in a shadow zone where no P waves were detected, which told us that there was this refraction occurring due to the core. So no direct P waves are observed over in this area. They used that information to calculate the shape and the size of the core, using a lot of math, and the source of data on interior makeup of the core. Okay, so this is how we know about the core. We don't really have the ability to get samples, the ability to study another planet like ours, so we have to rely on things like waves, which is a physics phenomenon that we can study in a lab and understand, and then apply that understanding to something that's too big to visualize, like our Earth. So when we see S-wave seismic data, we see that S-waves were not able to pass through the core at all. So if we think about what we said about S-waves, we said that S-waves cannot travel through liquids. So what that tells us is that the core must be liquid, because it doesn't allow S-waves to travel through. It has this huge shadow zone, okay? So this is how we determine that the core probably has two parts. There is probably a liquid outer core, which is protecting the S waves from passing through, but there's a solid inner core, which is what allowed the refraction of the P waves to occur. So this is supported by S and P wave data, but it's all theoretical based on physics phenomenons that we've studied in a lab. Other core evidence that we have are iron meteorites. They are made mostly of iron or iron-nickel alloy, and we think that it probably mimics the chemical composition of our core. We know that Earth has a magnetic field, and we know that the source is a turbulent flow within the liquid core, so there's a requirement to have a magnetic field as big and large as ours for the size of our Earth, that we must have a pretty large and powerful core, like a battery, at the center to power that magnetic field. And we know that the material must conduct electricity. So taking something like magnetism and electricity and studying it, we're able to apply that to the Earth and kind of hypothesize what we think is happening, but we never really will probably know 100% that we're right. Between the meteorite and the magnetic field data, it's consistent that we have an Earth that's made up around an iron core. So there are two layers of Earth that we don't typically see unless we're specifically looking at geology, which is the asthenosphere and the lithosphere. And so if we look here, we take a slice out of the crust of Earth, and we can see here we have the crust, the uppermost mantle, the asthenosphere, and then right here on this side we have the lithosphere. Okay, so the asthenosphere is going to be the bottom orange layer. It's thin, hot, elastic, semi-liquid material in the upper part of the mantle. It's distinguished by a sharp decrease in the seismic wave velocity, so waves will slow down when they hit the asthenosphere. The layer above that is the lithosphere. This is the solid layer above the asthenosphere. It includes all of the entire crust, the moho discontinuity, and the upper mantle. And it's made up of rigid plates floating in the upper mantle. And so essentially you have this solid plate floating on something liquid. And as you can probably guess, this is going to give rise to something like plate tectonics. So what is the theory of plate tectonics? It is a theory because we don't truly know, but we're basing it on a lot of geologic and biological evidence. So the theory of plate tectonics is that each individual continent will shift positions on Earth's surface. The patterns between the continental shapes can be fit together. All of these at one point were part of a single large landmass called Pangaea. Okay, so essentially they took them like puzzle pieces and fit them all together and said, hey, there's a bigger puzzle here going on, and called it Pangaea. However, there is evidence that the continents have been together in more than one arrangement. Pangaea is just the most recent one that we know of, but there were probably supercontinents before that time. But it's all based on the same kind of evidence we're going to see. Now, the original concept was called continental drift, which suggested that continents were simply drifting about without any real order or science behind it, but that isn't what's driving the movement of the plates. And so the theory of plate tectonics replaced continental drift. So what evidence do we have for that? Well, some of the evidence comes from the Earth's magnetic field. Igneous rocks will record the direction of the Earth's magnetic field, its strength and direction at a given moment of time. So the magnetite poles locked into the alignment with Earth's field upon crystallization. So if we can get layers of magnetite and look at the direction of the Earth's magnetic field, we can see how it changes over time. And so what we've been able to see is that Earth's magnetic field varies in strength and direction over time. And there's been over 22 reversals in the magnetic field over the last 4.5 million years. So if we see here, these are the oldest layers. These are the newest layers. And the directions show us how these electrons align with Earth's magnetic field. And you can see here that the layers, every once in a while, show a flipping. Okay? So the magnetite crystals preserve the orientation of Earth's field. So it's something that we can study. Evidence from the ocean. Well, we have some neat features in the bottom of the ocean, which, if you remember, we don't know a lot about our ocean yet, and I don't think we ever really will. But we do know that there are some features that suggest that the theory of plate tectonics is probably valid. One is the oceanic ridge. These coincide with submarine underwater earthquakes. There's a rift along the crest. Large amount of heat escapes from the crest and the mid-Atlantic ridge. So this is the mid-Atlantic ridge right here, okay, which is essentially where the Earth is kind of breaking apart. It's kind of like where new crust is being formed. So if this is continually moving out, what that means is the continents are also moving out. It can't just be the ocean moving. We also have oceanic trenches, which are long, narrow, and deep troughs with steep sides that always run parallel to continental edges. So right along the edges, we have these things called continental trenches, something we observe along the perimeter of our continents. This also suggests movement. Okay, same thing if you took a mountain or a bulldozer and pushed a bunch of dirt, you're going to have noticeable differences that can be attributed to movement, and we can see those underwater. So this leads to the seafloor spreading hypothesis, which is centered around the mid-Atlantic ridge. What we think that happens is that hot molten rock moves up from Earth's interior and emerges along the rift. It outflows in both directions, creating brand new rocks. And we have drilling evidence to support this. We have thin sediment layers near the ridge, becoming thicker towards the continents, suggesting that there is an aging process occurring. We can see older fossils and rocks near the continents, but they become younger as we move away from the continents towards the rift, so the mid-Atlantic ridge. You can see here that they've dated the rocks under the ocean, that these are the oldest out here, and then the newest ones follow all the way up to the mid-Atlantic ridge. So the theory is that the seafloor is spreading, which is producing new crust. We also see that there is magnetic seafloor spreading evidence. So if you see here, this is the oldest, the purple down here is the newest. We have paleomagnetic patterns of magnetic strips in the ocean floor basaltic rocks, identical to the magnetic reversal patterns on both sides of the ridge, so the evidence supports each other, which doesn't always happen in science. The patterns match those found elsewhere, providing age determination. So because we can match these rocks to somewhere else with a known amount of time, we can deduce the age of the rocks of things that are much, much, much older, coming from sources underneath the ocean. So lithosphere plates and boundaries is the basis of the plate tectonics theory. The lithosphere is broken into fairly rigid plates. We can see those plates right here in the different colors. The plates float or move on the asthenosphere, which is that liquid layer. Earthquakes and volcanoes and other rapid changes in Earth's crust occur most often at the plate edges. So if we look here, this is the Ring of Fire. I'm going to get this one wrong. Might have it wrong. It's hard to see the continents with the colors too. You have the Andes Mountains. You have the San Andreas Fault right here. You have, here it is, the Ring of Fire. Okay. I'm going to have to look. I think I've got that wrong. So then you have over here, this is India, and where you have, okay, this is right. This is the Ring of Fire over here. Sorry, guys. To the west of North America. And then you have over here where we have India, where there's known to be tsunamis and lots of earthquakes, very active geologic areas. So we have 3 plate motions which are important to us: divergent, convergent, and transform. Divergent boundaries are where 2 plates are moving away from each other, so they're diverging. Molten material will rise up out of the mantle as a result of the moving apart, and that happens to fill the fissures, to fill the breaks. Okay, so new crust is formed here. This is a new crust zone, often accompanied by volcanic activity, with the prime example being the Mid-Atlantic Ridge. In fact, you can see the Mid-Atlantic Ridge if you were to ever go to, let's go back and I'll show you, to Iceland. The Mid-Atlantic Ridge cuts through Iceland, and you can actually walk along the Mid-Atlantic Ridge, walk in it. Okay, the rest of it is underwater in the bottom of the ocean, and it's very hard to see. But in Iceland, it is visible on land. Convergent boundaries are the opposite. They are where 2 plates are moving towards each other, and at this place, old crust is destroyed. So this is the recycling center. That's what I call it, because we're taking old crust, recycling it, and then it goes back into the mantle, which then later rises up somewhere else and results in new crust. It's also called a subduction zone because one crust is going to be subducting under another, meaning one crust is going to go down into the mantle and be recycled, and the other one is like moving on top of it, kind of covering it up. Subducted materials partially melt and joins the mantle. Those elements then go down into the mantle and will be down there until they submerge over in a divergent boundary. There are 3 possibilities for convergent boundaries. We have continental oceanic, 2 oceanic plates coming together, and 2 continental plates coming together. Because continental and oceanic crust are different, remember continental is granite, less dense, oceanic is basalt, heavier, we're going to have different features that are going to form at these boundaries. So in an ocean continent plate convergence, so we have ocean right here, continent right here. The more dense oceanic layer is going to be forced down underneath the continental crust. So essentially, this is acting as a bulldozer. It is running over the ocean. And so what's going to happen is there's going to be a deep oceanic trench, so seen all along here. There's going to be deep-seated earthquakes, and there's going to be volcanic mountains. So these are the Andes down in Peru, okay, where we have the convergence of the South American plate with the Nazca plate. We also see this up in the Cascade Mountains in Washington and Oregon. Those are 2 common examples of an ocean-continent plate convergence. The next one we have is when 2 ocean plates come together. This is not the right image. Oh, no, it is. I'm sorry. I was not looking at the left. Okay, so we're going to have the trench and the underwater ridge created by subduction. So in this case, it's just kind of a matter of who's probably been there longer, who's going to win out the race. Anderson, please, you're going to knock the water over. Okay. Sorry, I have a 5-year-old who's also at home with me. He's climbing on the bed, and I think he's going to knock his water over. So you're going to have one layer getting shoved down underneath. You're going to have that same trench. You're going to have the deep-seated earthquakes, but you're also going to have deep-seated volcanoes, okay? And we tend to call those island arcs, where we're going to have mantle that's basically breaking through the ocean floor to form volcanoes, which eventually will form islands. And so Hawaii is a great example of an ocean-ocean plate convergence. So let's go back and look at the map where we have, oh, it's so hard to see. I think, if I'm not mistaken, right over here. I draw all over it and I don't know how to erase it. Oh no, come on. Okay, let's just start that over. Okay, it's going to get rid of all my markings. That's one of them, and then the other one that I can think of are the islands up in Alaska. But I cannot think of what they're called right now. I'm going to have to look it up because it'll bother me. Island arcs. I'm going to have to come up with it later, and I'll have to write it down. But there are some up in Alaska as well that are an example. That bothers me. All right. Continent plate convergence. So when we have granite and granite coming together, they're both of equal density, equal mass, and they're both continental. So because we have less dense granite type materials coming together, they're going to resist subduction, meaning one is not going to go over under the other and one is not going to go over the other one. So because of that, there's no preference for one plate to fall under another one. The colliding plates instead are going to pile up and up and up and up, producing a deformed and thicker crust of lighter materials. So these are going to lead to things that we like to call mountains. Not the rolling hills we have in Texas, but true mountains. The Tibetan Plateau and the Himalayan mountains are some of the more common examples of two continental plates coming together to form mountains. And you may be asking yourself, well, then why aren't mountains getting increasingly taller over time if this is happening? And that's because there's a process called erosion and weathering. So as mountains are being built up, they are also being worn down. So it's kind of a homeostasis process. It's keeping everything the same. Last boundary is transform. So we had one type of divergent boundary, three types of convergent boundaries, and then transform. So transform boundaries are where two plates are not coming together or coming apart, but they're simply passing by each other, sliding past each other. The crust is neither created nor destroyed in the process, but there are irregularities in the movements along the boundaries, which, when they're sudden enough, can produce an earthquake. The most common example here is San Andreas Fault along the California coastline. Is where you're going to have, I just thought of which other islands. The other example is the Aleutian Islands. But I can't remember. I think it's Aleutin, the Aleutian Islands. I knew that was going to come to me eventually. All right, oops. So the San Andreas Fault. So you have two plates sliding past each other. They're kind of, it's like getting your shirt stuck in a car door or something like that. They're eventually you pull hard enough, you're going to pull your shirt out, right? And so the two plates will be basically locked into each other, and eventually enough energy builds up and they're going to pop. And when they pop, that's going to produce an earthquake, and then it's going to stop and it's going to build up again. So because of that process, the building up, geologists can monitor the activity around an area like San Andreas and tell when there's going to be a big earthquake, because they monitor the energy behind the movements of the plates pretty closely to make sure that they don't get caught off guard with a major earthquake. But that's why areas like California have a large number of earthquakes, is because the San Andreas Fault is present there. All right, so this is all of chapter 15. I hope that you paused and filled your notes in as you went. This will be the first chapter on the exam 4, which I'm hoping by that point we will be back on campus together to finish out this semester. Please email